Hello, good morning. Welcome to this lecture. Sorry about the delay. Um, I see there are 71 of you here, so that's not too bad. We were looking at ADC's analog to digital converters last time, and we looked at the digital ramp, ADC, which I think is quite easy, and everyone got how it works. But essentially, you have a scenario where you have a counter that counts from 0 towards its maximum, whatever its maximum is, depending on its number of bits, and you keep comparing the output. So the output of the converter is converted to digital, um, is converted to analog using a digital to analog converter here, and so you're comparing VAX with VA. VA, when VA is greater than VAX, you have a high out of this comparator. And so here, EOC will be high. Until VAX is greater than VA, then you have EOC is a 0. And when EOC is 0 here, we can see that EOC is actually active low. So when it becomes a 0, it goes into this AND gate. And because you have a 0 going into the AND gate, what goes out of here will always be a 0 irrespective of what's happening at the clock or this other side. And when you have a 0 going into the clock, it means you'll not get clock signals. And that also means the counter will not count. So that when EOC becomes 0, the whole system understands that the conversion is over because this is the end of conversion signal. And then you can, the counter state at that point is equivalent or is taken to be equivalent or to be the digital equivalent of the input analog signal VA. And so usually you have this connected obviously to a computer or some memory. And so that that signal can come out and go into storage or any other purpose that you want to use that for. Excuse me. Yeah, that goes into storage, and when you want to restart to convert another signal, you give a start signal and the whole process repeats again. So that means that if VA, let's say for instance that you have a counter that counts from 0 to 16, and let's even assume that the resolution is 1 volt, meaning we go from 0 to 1 to 2 up to 16, up to 15 in fact, not 16. It means that if VA is about 2 volts, then we will need 3 clock pulses, okay? And so we will convert this using 3 clock pulses. Remember that when VAX is equal to VA, we still need to go a step. In fact, what we want is that VAX should be greater than VA plus a certain threshold voltage. All these things we've talked about them. If VA were 10, we would need 11 clock pulses, okay? And if VA was say 14, we would need 15 clock pulses. So that shows you that actually the speed with which the conversion takes place in this case is dependent on the value of VA. Since every time we try to convert a signal, we start from 0. The counter starts from a cleared state and counts upwards, meaning that we are going to take longer if the value that we are trying to convert is high, compared obviously to the full scale of the converter, of the digital to analog converter, as well as the resolution. Okay. So we had looked at some of these. Now we want to look at something that is you probably already know this, because obviously here we have an analog signal. We try to convert it to a digital signal. Let me ask some of you, especially the telecoms people, if you have ever heard of if you've done something called pulse code modulation. Have you done this? You can, yeah. Somebody says no, not yet. Okay, so because if you haven't, then I need to teach it a bit more detailed. Anyway, so when we are trying to convert a signal from analog to digital, this is something you study in communication engineering. I don't know who teaches that now, maybe digital engineering. But I'm going to try and teach you how this works. So you have, let me make a copy of this. So we want to convert a signal that is analog. We want to convert it to digital. We start off with an analog signal. We look at its maximum amplitude and its minimum amplitude. Okay, this is the amplitude, and our signal is moving like that. We know that this is the minimum amplitude. This minimum amplitude could be 0, but it doesn't have to be. And we know that that is its maximum amplitude. Let's take it to be equivalent to that. Now, when we are going to convert an analog into a digital signal, we perform a process that is called sampling. Sampling is a process where you take samples of the signal at every other point. And so in this case, we could say that we are going to take a sample of the signal at this point. Then we are going to take a sample of the signal at that point, another sample at that point, another sample at that point. A sample is just a magnitude of the signal. So, you have like a measure. And so every 1 second, you can take a measurement of the signal because you see the analog signal is changing. So the idea is that the sample that you took a second ago is not going to be exactly the same as the sample you're taking now. It could be if the signal is constant, but we know that the analog signal is usually changing. So we take samples at every different intervals. And so this signal might drop back. We continue taking samples at different times. This is called maybe T0, T1, all the way up to Tn, right? This is called the process of sampling, where we take samples of the signal. The idea with analog is that we do not need, if I'm like, this is my analog signal and I take a sample here and I take a sample there, the idea is that I don't need to know these values of the analog signal. Remember the analog signal, these values could be anything. They could be any, the idea of an analog signal is that it's continuously changing and it could take on an infinite number of values within that. But the idea is that if I can take a sample here, I take a sample here, and then I take another sample here, then I don't need to know these values in between for me to be able to reconstruct the signal. In other words, my digital equivalent of this and that, which is, I'll say digital, and if I take these digital values, there'll be enough for me to have captured enough to reconstruct the signal or to decode the signal, understand what it was about. Okay, so this is the process of sampling. We don't need to know the whole signal. We just take samples at specific intervals in time. Now, these samples, there's a theorem that manages this sampling. In fact, this is called a sampling theorem. Sampling theorem. There's like a rule that you must follow to perform this sampling. It is not a matter of just sampling. And this sampling is about the rate. At what rate should we sample? What should be the difference? The rate, rate is 1 over time, really. A rate is like a frequency. What is the frequency or the rate at which we should take samples? Sampling theorem manages that rate. So it tells you, okay, so if this is the signal, should be its rate. Does anybody know that sampling theorem, what it states? The sampling theorem, it's also called the Nyquist theorem. Nyquist is a guy that found out this theorem, so it's also called after him. It's named after him. Anybody knows? If you don't know, yes, let me just state it for you. It states that if an analog signal has a maximum frequency FM, okay, so we know that an analog signal can have I don't know, if you look at your signal in the frequency domain where this is amplitude and that's frequency, you might find that at that point, this is my FM or F max, basically. That will be the frequency maximum. So for instance, if you're looking at voice, I think I've mentioned this before, your voice, my voice, everyone's voice usually ranges from around 300 Hz frequency to around 3,400 Hz. So this is the maximum frequency I'm referring to in this theorem, that if an analog signal has a maximum frequency FM, the sampling rate Fs should be greater or equal to twice the maximum frequency of the signal. In other words, you should sample at a rate that is at least twice the maximum frequency within that signal. Yes. So Gilbert has put it in the chart, a periodic signal, even if it's not a periodic signal, even if it's any random signal, it must be sampled at more than twice. In fact, it is at least twice. You see that the language is important, at least twice. So if you sample at twice, exactly twice, that's okay, but make sure that it is at least twice or more. If it is less, we are going to have a problem, and we are going to see this problem where it comes from. So if I was sampling a voice signal, it means that this signal should be sampled at a rate that is greater than or equal to twice times 3400. So I could sample at 6800 or greater, right? That means my sampling rate is obviously samples per second. Now, in fact, in the old telephone systems, the desk telephones, you might have one at home if you're rich. The old telephone systems sample at around 8,000 samples per second. And you can see that this 8,000 is obviously greater than 6800. We are going to see that the higher the sampling rate, obviously it has an effect, and I'm going to describe what kind of effect that is, but make sure that you sample at least twice the frequency of the signal. Okay, I need another copy of this. So now let's say that we have a signal like this. We know the rate, we know this speed and that. We know the maximum amplitude and the minimum amplitude as that one, all right? And we have taken our samples, and our samples are taken at a rate that is in line with the Nyquist theorem, so at least twice the sampling rate. If we do that, if we sample at least twice, then it means that we will be able to reconstruct the signal and intelligibly decode it. If we do not, we are going to have a problem, and we're going to see what it means. Now, then once we take the samples, how do we encode them? That is the process of encoding. When you're encoding something, you're getting a value and giving it a code. In this case, a binary code, if we are doing binary digital conversion or some other binary code, but let's do binary. So usually you get this range and divide it into something we call quanta. Quanta is like, you quantify. So the quanta comes from the quantification of different levels. So let's say, for instance, that I want to do 2-bit binary conversion. If I want to do 2-bit binary conversion, it means that samples can either be 00, 01, 1, 0, or 1, 1. So I need 4 levels, 1 level, 2, 3, 4. It means the any sample that is in this range will be 0, 0. Any sample in this range is 0, 1. Any sample in this range is 1, 0. Any sample in that range is 1, 1. So when I take my sample here, I already see that this sample is in this range. So I'll give this sample, encode it as 0, 0. So you have a sampler, it takes a sample and compares it with your quanta and encodes it into some digital signal. This sample here is still in the same range, so I'll call it 0, 0. That sample here is in 0, 1, so I'll call it 0, 1. That one as well, even this one, and that one is now in 1, 0. Okay, so I can call it 1, 0, and maybe this one as well, 1, 0, and finally 1, 1, right? So my analog signal between this range, between this point and that point in time, can now be represented by a digital signal that is 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1. Okay. If there was another sample and maybe at this point the signal comes down, I take another sample here. I can call it 1, 0, another sample here, maybe 1, 0, another sample here, 0, 0. And so I can just continue doing that, 1, 0, 1, 0, 0, 0, and so on and so forth. Now, your encoder knows that each sample is being encoded by 2 bits. Your decoder also should know that your encoder used 2 bits. So your decoder will also be 2 bits. And so every time it looks at 0, 0, it will give it a certain value. If the next 2 bits are 0, 0, it will give them a certain value, 0, 1, and so on and so forth. Let us look at what happens on the decoder side. Okay, so that is how we do that. If I give another example, okay, so maybe now I can use we have a sample, a sample, a sample, a sample, 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 sample. Now, let's assume that I was instead, before I used the 2-bit coder, now let me use a 3-bit coder. It means that my samples can be encoded into 000, 001, 010, 010, 100, 101, 110, 111. So here I need 8 levels. 1, 2, 3, 4, 5, 6, 7, 8. So this level will be 000, 001, 010, 011, 100, 101, 110, and 111. Now you should note that in the scheme that I'm using, here the quantization levels are the same. So the size of these steps, the size is the same, although here you can see there is a difference because obviously I'm not accurate, but we should remember that these are the same. There are schemes of quantization where the levels may not be the same for certain reasons, and if you were doing this in communication engineering, I would explain all of that detail. But here I just want to give you enough knowledge to understand what is happening on the digital electronic side of things. But here, let's just assume that all these levels are supposed to be the same. Now it means that when I take my first sample will be 000. The next sample will be 001. The next sample might still be 001. This sample has now become 011, so meaning there is no sample that is taken in this range, because remember we are taking these samples periodically. When we get our FS as maybe 2 kilohertz or 2 kilosamples per second, it means that we are going to be taking a sample. Clearly this is a frequency, and a frequency has a period. And so we are following a certain period. We are taking at specific intervals, irrespective of where the signal is at that point. If we take this one, maybe this is 101, this is 110, and finally 111. And so this signal can then be represented in digital as 000, 001, 001, 011, 101, 110, 111. This is something that I can now feed into a computer, and store or process and so on. And so really this is what happens in something like digital audio. I think you've probably heard of something like digital audio processing. When you store your audio in the computer, we know that audio, like a song, like music is analog. Music is analog in nature, but you cannot store it in a computer in its analog form. We have got to convert it into digital. And so this is what happens. You sample that analog audio and create a digital signal that you store in the computer, or your MP3s, or are the digital format, so the digital equivalents of analog signals. Now, when you are going to play your audio, you are going to play your MP3, what happens is that you get this and convert it back to analog. Convert to analog. And so your audio player usually converts this to analog, and that's why it's able to come out as an analog signal in the in your speakers. Now we need to understand the analog signal that you get is like an equivalent of the original analog signal, but with some small differences or errors, because as we are going to see just now. So let us look at our signal again, and we are going to use a 2-bit 2-bit. So we have a level 000, 001. No. This is just 2 bits. 00, 01, 10, 11. So I should mention here that before we go, that you can see that usually when you do two bits, if we were doing, for instance, here, if we did 2, 3, 4, if we did 2 bits, you see that the jumps are big. But if we had chosen here to do 3 bits, we would have 2, 3, 4, 5, 6, 7, maybe 8. You can see that the jumps would be smaller. So it means that the bigger the number of bits you use, the smaller the size of the quanta, the smaller the size of the step. And usually that makes it more accurate in your approximation. Because you see, if I have a sample here and a sample here, all of them will be taken as 00 and 00, yet they are not the same. However, in the case if I was using this one, that sample would be taken as 000, and that sample would be taken as 001. So you can see that now we are able to differentiate these two, and this enhances accuracy. And so if we want to increase the accuracy of our conversion, we increase the number of quanta. We increase the number of steps that we divide, or that we divide or encode our samples. If you increase the number of bits per sample, this is what happens, because in all cases the number of samples will be the same. If you increase the number of bits per sample, it means that you are increasing the total. So for instance, you're increasing the total signal, the total digital signal, the size of the digital signal. So for instance, if we are using 2 bits, for these 2 samples, we would have 0000. But if we are using 3 bits, now we have 000, 001, 6 bits instead of 4 bits. Obviously, 6 bits take more time to process. They also need more storage capacity and so on, but they give you more accuracy. So you can see that there is a trade-off between how many bits you should use vis-a-vis the memory, the processing power that you have, and so on and so forth. Okay. Let us look at the decoding side. So now I have taken my samples as this one, that, and that. And so my sample here is taken as 00, 01, 10, 11. Now this is my digital signal, 00, 01, 10, 11. When I come to decoding, I still remember my sampling rate. I know that each sample was taken at a certain period like that. But while this was 00, this was 01, this was 10, and this was 11, I know that my first sample of 00 was taken at this point, but I don't know where along here it was taken. Okay, I don't remember. It is not possible to know that it was at that height or at that height or so on. All you have is the range. So here, what I can do, okay, I'll rub that. Here, what I can do, these are my sampling points. You can say, okay, if I find a 0, 0, I'm going to record it in the center of this range. Okay, so I can put my signal in the center of that range. The next sample was taken at this point and it is 0, 1. I can put it in the center of this range. The third point was taken as 1, 0. I can Hello, I'm sure you probably lost me there. Can you hear me now? Okay, great. Yeah, someone was trying to call. So on the third sample, this is T1, sample 2, sample 3, sample 4, and so on. On the third sample, I have 1, 0, but I don't remember exactly where 1, 0 was. So I will come to the center and take my sample there. And T4, I will also come to the center and take it there. And so now my signal looks, I will now connect these points and have my digital signal. So if you compare these two signals, you can see that they are not quite similar. They are not very similar because this one has a bit, it's more curved here and then more curved there, whereas this one is almost close to linear. If we want to prevent this issue, we increase the number of bits. So this one obviously leads to more error if your bits are few. Let me also just mention that, for instance, here, let us say that we took, okay, we have a signal here and we have a quantization like that, and our sample was taken at this point. When I'm decoding, I don't know at what point the level was, so I will put my sample at this point. The difference between this level and this level is what we call the quantization error. It is that although I have a range that is, for instance, 1, 0, if my sample was taken, it was actually at this point but falling within range, when I'm decoding, I'm going to force it at that point. And this range is what we call quantization error. Once you decode this, and so really, if you want to manage quantization error or to reduce it, you should make sure that the size of these jumps, of these steps, is small, so that you can reduce the possibility, or you can reduce the difference between where the original sample was, the actual value was, and where you put your quantization error. Some other people do it like this actually. And so this is not strange, T2, T3, T4. If this is your your 4 jumps, now instead of putting it in the center, they put it at they can put it at the top here or at the bottom here. The next sample will be put there, the next one will be put there, and the other one will be put there. I think when you put it in the middle, the quantization error is smaller. Let me explain why. If you put it in the middle, let's say, for instance, that this is your jump. If the sample was at this point, you can put your approximation in the center. This will be your approximation error, or so-called quantization error. Now, if for the other scheme, this sample was here, but now it is approximated at the top, you can see now that this error is much much bigger than in this case. Here the error is halved, whereas here the obviously I'm looking at the maximum error, but you might find the sample was taken there, in which case the error will be small. We are really looking at the maximum possible quantization error in this case. Anyway, so do you have any questions before now we go back to digital electronics? Okay. Good that you've got this the first time. So when you meet it in your telecom course, it will be very easy for you then. So now we can say, for instance, in the case where we were looking at, I have my level here, and I'm taking the highest point or the minimum. I could say that if this is my level 00, when I'm decoding, I will put my approximation either at that point or at that point. It means that the maximum error, maximum quantization error, sometimes they quote it as +1, +1 lowest significant bit. I think you remember the units of the low significant bit, the weights of those most significant bit, low significant bit, and so on. Because if for instance I'm taking this to be, if I'm taking this, let me say that I'm taking it at that point, whereas maybe my sample was at this point. We are trying to create a scenario where the error, the quantization error, is maximum. It means that the error here is about one step, and we know that one step is equivalent to the weight of the low significant bit. So it means I could create an error. It is possible to create an error that is equivalent to the weight of the lowest significant bit. If the lowest significant bit is, its weight is 1, then I've created an error of 1 volt. If the maximum weight is 0.1 volt, then my maximum error is likely to be around 0.1 volt, and so on and so forth. Now, in the scenario where the other scenario where we looked at the fact that I am taking the midpoint as my approximation, even if my sample was at this point or at that point, you can see that the maximum error is only likely to be half. And so here I can say that my maximum error in this case is plus or minus, not plus or minus, but plus 1/2 of the weight of the lowest significant bit. So if I tell you that, if I give you a question and I tell you, assume that the quantization error is plus half lowest significant bit, all you need is to find the weight of that and then multiply half, or you find, if it is +1, you find the weight of this one, you multiply 1. Okay, so these are the two scenarios that actually lead to these two cases. It is plus or minus. If it is really plus or minus, so we can do that, and so you would know that for plus we are looking at the upper side, and minus we are looking at the lower side. Okay. I mean, it is an error, so we have to. You're right that we have to look at it in both sides. Okay, so just one moment. Yeah, so really the error is you could say plus or minus a half lowest significant bit. I think conventionally they just plus a half lowest significant bit, but I think this is less confusing, so to speak. But we need to remember that this can happen on the upper side or on the lower side. But if I think in this case this applies, but in this case it may not apply, because you see here we are taking the upper side, And so you could also take the lower side, as I said earlier. And if I'm taking the lower side and my signal is up here, then it means that I always have a positive 1, a maximum plus 1 low SB. I think this is where that nomenclature, that kind of standard nomenclature comes from. The fact that the error is on the upper side. That is if you are taking the lower value as your approximation. But where your approximation is in the middle, it is right to say plus or minus a half LOSP. Right. Okay, let me duplicate this slide. Okay. Now let us look at the specified error. The specified error is actually something that comes from accuracy. You see, the problem with these things is that they are electronics, and with electronics you could have errors due to components may no longer perform effectively due to age, due to drift, drift in their performance over different issues, and so on. And so we have an error that comes from the accuracy. This is actually something we've looked at before, where we say that accuracy is expressed in terms of full scale, but usually this is with DACs. In analog to digital converters, it is usually expressed as plus or minus n LOSB. LOSB is the weight, and n is a number. N can be 1 or can be 2 or can be whatever. Whatever you want. And so, for instance, we could say that n can be 0 less or equal to n less or equal to 1. Okay, I think the idea is that if you're having your resolution and accuracy should be linked, because if you have a very good resolution but a very poor accuracy, then you have wasted bits, because you have many bits that give you a good resolution, but your accuracy is poor. So what's the point? Whereas it's also not necessary to have a very good accuracy when your resolution is big, because now the accuracy will be limited by the resolution. So these need to be a bit linked. So for instance, we could say that our accuracy error, this is called the specified error. It shouldn't confuse you. Can be a half plus or minus a half low SB. In this case, n is a half. N can be a quarter, so you can have 1/4 LSB and so on. And so now, because you have these two types of errors, you have an error that comes from the quantization and an error that comes from the specified. You need to add them together to reach a total error. So if I give you this, usually you would end up adding a quarter plus or minus low SB plus maybe a half plus or minus low SB, and this would represent the quantization error that comes from resolution. This comes from accuracy, usually due to the hardware components drifting. Let us look at this example. So we have a full scale input of 2.55 volts. Full scale is 2.55 volts. It produces a digital output of 1, I think this is 2, 4, 6, 8, okay? 1, 1, 1, 1, then 1, 1, 1, 1. So this is an 8-bit ADC. It has a specified error of plus or minus a quarter LOSB. Determine the maximum amount of error in the measurement. First of all, we need to get the resolution, because the resolution is the weight of the lowest significant bit. And so we know that the resolution is equal to AFS over 2 to the power n minus 1, and AFS is the full scale 2.55 over 2 to the power n n is 8 minus 1. So we have 2.55 over 255. Resolution is then 10 millivolts, or 0.0. Is that so, or is it 0.01? I think it is that one, 0.01. Now, the error, the quantization error is equal to plus 1 LSB. In this case, they have not really told us that we are using the middle point. So I think it is reasonable to assume this worst case, which is 10 millivolts. If they had told us that they are doing a half plus or minus a half LSB, then we would use we would take that as 5 millivolts, for instance. Now in this case, our specified error will be then equivalent plus or minus a quarter of the lowest significant bit, 10 millivolts, which is equal to 2.5 millivolts. So it means that our maximum error is 2.5 plus, and this is plus or minus obviously, plus 10 millivolts, which is equal to 12.5 millivolts. That is the error that you could actually end up with when you do your decoding, basically. Now, let me just also mention that if we had taken the other part of where our approximation is in the middle, and so our quantization error is plus or minus a half millivolt LSB, then our quantization error becomes plus or minus 10 millivolts times a half, which is 5 millivolts. And so we then add the specified error of 2.5 millivolts, and we would get 7.5 millivolts. Okay, so you can see that when we take this approach of approximating by the midpoint of the quanta of the quantization level, we have less error. But overall, for us to minimize the error that comes out of this, we have got to use we have got to use more bits so that those jumps, those steps are much smaller, and so that becomes very helpful. For instance, if we had okay, so these are 8 bits, okay, and we see that our resolution is 10 millivolts. If there were 4 bits, we would be in trouble, because then we have 2.55 volts over 2 to power n is 2 to power 4 is 16 over 15. What does that give us? Zero point 0.17 volts, which is equal to 170 millivolts. So you can see in this case that if you did your errors, you'll end up with a much bigger error, because you are using fewer bits. Okay. Now, how do we know the conversion time? Remember, we are comparing VA, X, and VA. Now, VAX, for us to end the conversion, should be greater than VA, or maybe greater or equal to VA plus a certain VT. So it means that, first of all, let us look at this question. What will happen to the operation of a digital ramp ADC if the input VA is greater than the full scale? In other words, your full scale is, say, 10 volts, but VA is, say, 12 volts. No, in fact, let me say 15 volts, just so that we can use actual numbers. let's assume that my full scale is 15 volts, but VA is 16 volts. Here I'm using a 4-bit ADC resolution is equal to 1. It means you have a counter that counts from 0000 to 1111. Even if it is at 111, which is equivalent to 15 volts, it means in this case, when it is at full scale, VAX will be equal to 15 volts, but VA is equal to 16 volts. In other words, VAX will always be less than VA plus VT. What happens here? It means that in this case, even when VX has reached its maximum, EOC will still be equal to 1 since the other scenario has not been satisfied. And as long as EOC is still equal to 1, the clock signals would come into the counter and the counter will continue to count. It means in this scenario, the counter will count forever. You will never convert a value of analog signal that is greater than the full scale of the counter. In this case, you would need a larger counter that counts up to 31. Therefore, if we look at this, it means then that VA should be slightly less than, VA should at least be equal to, should be less than the VT plus, no, I think I need to restate this. I should mention that VA should be less than the full scale minus VT. In other words, if full scale is, as we have seen, is 10, is 15, and let's say VT is 1 volt or 0.5, let me take it as 0.5 volt, then VA should be less than 14.5 volts. This is the only way where it can be converted, because it means that at some point when VX is at 15 volts, it will have satisfied that condition. Anyway, so we see that actually we should never try to convert a value that is greater than the full scale of the counter in the digital ramp in this case. As we are going to see, this is not a problem for another converter that we are about to look at. However, it means that the maximum conversion will happen when VA is close to full scale. In other words, you need VAX to reach its maximum level for the conversion to happen. This is when you're going to have the maximum conversion time, and that will take 2 to the power n minus 1 clock times. So for instance, if we are looking at 111, it will have taken 15 clocks. And so we can say that TC max is equal to 2 to the power n minus 1 clock times. And so maybe my F clock is 1 megahertz. If it's 1 megahertz, each clock time is 1 microsecond. It means, once 1 megahertz is 1 million samples per second. It means each clock time is 1 microsecond. And so in this case, my conversion time would now be 15 microseconds. Sometimes, because the signal does not always, VA does not always have to be close to the maximum. It can be very low. It can be in the middle. It can be in it can be in the middle. It can be up there. So sometimes we take the conversion average time, which is a half TC max, or a half of 2 to the power n minus 1 clock times. And apparently this is also equal to approximately 2 to the power n minus 1. So in this case, it would be 2 to the power n is 5. N is 4, sorry. So 2 to the power 3, which is 8. So you can see if we took this, that's why I've put approximately. If we took that, we would have a half times 15, which is 7.5, which is actually approximately equal to 8. So you can say for the average case, 2 to the power n minus 1, whereas for the maximum case, it is 2 to the power n minus 1. Okay, big difference. Right. So we have something that we call data acquisition, and this data acquisition is something that happens, for example, in audio, digital audio processing, where you have an audio signal and you keep taking its digital equivalent. And so when we use the digital ramp, we can have our computer connected to the digital ramp. The computer gives the start signal, and when the computer gives the start signal, the signal, the digital ramp starts to convert this input analog signal. Remember, this input analog signal is now a music. It is like voice or music. It is changing. And so this thing will start to, it will take a sample maybe, or at least it will start to change. It can take a sample and begin to change that sample to convert it into digital. And you can see that actually when it receives the start signal, it begins to jump. It begins to go through the staircase until that requirement that VAX should be greater than VA plus VT is met. That's why it goes slightly above it. When that is met, the EOC goes 0. The microcomputer notices that the EOC is now equivalent to 0, and it knows that the conversion has ended, and it will pick up the signal that is within the counter. Remember, there is a counter in here. That digital equivalent will be stored in the microcomputer, and then the microcomputer will give another start signal so that the digital ramp starts to convert the next sample. It will convert until it meets the analog signal, and it will give an EOC of 0, and then the microcomputer will pick up that signal and keep it, the digital conversion, keep it in its memory, and give the next start signal. And so that is how you get your analog signal converted into digital signal and stored within the computer. There's a problem with this process. Unfortunately, there's a problem with this, because you can see that in this case, it has taken time t1, in this case time t2, in this case time t3. And all these times are not the same. Clearly because the conversion here, the time depends on VA, the size of VA. In the first case, VA is very high, so T1 will be longer. VA has reduced at T2, so T2 is slightly is that little bit smaller, and T3 is even smaller. This might end up abusing the theorem that we talked about earlier, but it is something that can work depending on the ranges you're working within. But generally, this is something that we call data acquisition. And so this is actually something that we have already looked at. And so you have your points here, A, B, C, D, and the actual voltages at those points. As you can see, you can find your actual voltages at those points. They have been put in this table, okay, that, and they are equivalent digital values. They are equivalent digital values once you've been doing the conversion. I think these are 8 bits, so you're looking at 8 bits. Now this is the part that we have already looked at. When you are reconstructing the signal, when you're reconstructing the signal, you don't know, you have created quantas. You don't know exactly where that signal within that range was. So you can just, at that point, you draw a level line and a level line and a level line and so on. And so technically you would be having a signal that is like this. But the good thing with electronics, and usually you would maybe, jump steps, you'll find your signal is like that most of the time. But actually what the good thing with this is that when you pass this signal through a filter, an RC, a simple RC filter with a capacitance and a resistance, it smoothens it out. And so you end up with this signal. It removes those sharp edges and smoothens it out, but still it may not be exactly similar to the original analog signal. The only way we can ensure that it is impossible to ensure that they are similar, we can only bring them as close to each other in similarity as possible. And the only way we can do that is by by increasing the number of bits. So if you are using 8 bits, use 10 bits, use 12 bits. The problem with that is that you have more bits to store, and so there's some kind of trade-off for you to consider. Any questions before we move to something else? Okay, if there are no questions, let us look at something called aliasing. Aliasing is something that we consider when we are doing our sampling theorem. So we say that we should sample at least twice the frequency of the maximum frequency of the signal. Okay, that's what we say. The Nyquist theorem states that when we are sampling a signal, an analog signal, we should sample it at least twice the maximum frequency within that signal. So if my maximum signal is Fmax is 10 kilohertz, then my sampling frequency should be greater or equal to 20 kilosamples per second, or kilosamples per second. This is actually sometimes you could confuse that with kilosymbols per second, but and we know that this works within the say QAM, QPSK, and so on. But yeah, in this context, it means kilosamples per second. Now sometimes signals actually never end. So you have a signal like this that just continues on and on and on. And so what we do is, if we want to sample, we come and filter. We filter out this, and then we sample at twice this frequency. So sometimes they do that. They perform some kind of filtering to make sure that the frequency of sampling is not too high. Now, what happens if you sample at a frequency that is below the actual sampling frequency? So for instance, let us assume that in fact there is a component that is at 12 kilohertz instead, but yet we have sampled at 20 kilohertz. What actually happens is that you create an alias of the signal, an alias of that component. And what happens is that this process is called aliasing. It is an error, really. It is not a process, it is an error. So if we do not follow the Nyquist theorem, we will suffer from a process called aliasing, where an alias of the signal actually happens. And so the alias would be the alias will be created, alias frequency, and the alias frequency will be created at the Fs, the frequency of sampling, minus that component, frequency component that appears above what we took as our maximum frequency component. In this case, it would be 20 minus 12 kilohertz. This is, you could say 12 kilohertz here, which is 8 kilohertz. Now, it means that, you see, the sampler will not ignore the signal. For it will sample. The digital sampler does not know that there is a signal that is above the 10 kilohertz. So it will sample, and then it will create, there is going to be a mixing of those signals, and you're going to end up with a component at 8 kilohertz that was not there. Even if there was something at 8 kilohertz, this will be added onto that, and that is going to distort the signal. To be able to understand this, you have to understand this in your communication theory course. Okay, communication engineering course. I don't know wherever they teach this, but we need to remember here in digital that when we do not follow the Nyquist theorem, we are going to create an alias signal that is going to be found at the frequency that is the difference between the Nyquist frequency, or the sampling rate, and that frequency. So in this case, our frequency, the component above the maximum frequency is 12 kilohertz, and the sampling frequency is 20 kilohertz. And so we remove those, we take the difference and find that actually this alias will take place or will be found at 12 kilohertz. Let's see, let me make, right. Now let us look at this frequency. This frequency in yellow is taken at, it is a frequency, you can see it's a tone. A tone is like a signal with just one frequency. So like a sinusoid, so to speak. And its frequency is at 1.9 kilohertz. And so really the right fs should be should be greater or equal to 3.88 kilohertz or kilosamples per second. Unfortunately, you see they have sampled at fs of 2 kilohertz. You can see these samples at 500 microseconds. And we know that in this case, because the frequency of sampling is below the right one, we are going to create some what we have already called aliasing. And the alias frequency is going to be equal to 2 minus that signal, 1.9, which is equal to be 100 hertz. Okay, so instead of listening, when you finally reconstruct your signal, because obviously we are sampling so that we create a digital signal which we can convert back to analog. When you finally reconstruct your signal, you are not going to listen to you're not going to receive a signal of 1.9 kilohertz, you're going to receive a signal of 100 kilohertz. And actually, if you draw a line through these samples, you can see that that signal, the frequency is so much lower, and in fact, it is equivalent to 100 hertz. Okay, any questions? Okay, if there are no questions, I really hope that you have understood. I wanted to go to a different topic, but unfortunately I need a lot of time for it. And so I'm not going to continue. I'm going to stop here. We have done a 1 hour lecture, although it has started later than usual, but considering that we have just 10 minutes at your lunchtime, I think I'll stop here. We'll continue on Tuesday and complete this chapter by looking at one other analog to digital converter. I know that you have an individual assignment. Please work on it. We are going to, I think the submission is on Monday. Please make sure that you submit by Monday. I'm working on another group assignment for you so that I can continue to have you engaged. We are going to do a test, I believe sometime this month, hopefully towards the end. So please improve or ramp up your reading. Otherwise, have a nice rest of the week and see you next week. Okay. I think the assignment should be typed. This is very important. Make sure you type the assignment. Don't submit any handwritten work. And you don't have to bind. I don't want you spending your money on binding unless you want to, especially, but you don't really have to bind. If it is too much, don't bind. The assignment you can hand it, Maureen, you can hand this to anyone in 162, preferably Alex or do the instructions say handwritten? Let me see. either to Alex or Bena. Let me just check, because if that's what it says, let me see. Individual assignment. Okay, so if I said handwritten, okay. Okay, so yeah, I think it's because of the nature of the, okay. Okay, yes, you submit it handwritten, but please let it be clear. Why I prefer typed work is because, you know, it's very easy to see what the person is doing. Some people write badly. Okay, so you can submit handwritten work, but be neat, be precise, be concise. Otherwise, with handwritten work, if things are not very clear, you can easily lose marks if the person grading you is not able to understand. But yeah, you submit it handwritten. Thank you. Thank you for that. Okay, good. Have a nice rest of the week.